let's talk about momentum. This is chapter 9 material. Momentum is a fun thing because it's just saying that motion is conserved. So that is the general premise here, that motion is conserved. And we can define this motion in terms of something's mass and its velocity. So we call that, we say this letter P stands for momentum equals something's mass times its velocity. I don't know what's happening in the kitchen, but I think we're good. And if it's conserved, then that means that we can look at things comparing an initial condition to a final condition. So I can say that whatever I have initially is going to equal what I have in the end. And you have to know, like if I just wrote this, that mv initial equals mv final. Well, if my masses are staying the same, that whatever this initial velocity is would have to be my final velocity. Well, that's just no fun. So what we're going to do to make this more interesting is do things like crashing things into each other, letting them bounce off. So what I call an elastic collision, elastic. So that means bouncing off. Bounce, oops, there we go, bounce off. An inelastic collision then, inelastic is when they stick. So the way we can write these kind of in terms of this conservation then is to say for elastic, I'd have something that looks like this. I'd say, okay, so I have mass 1 has its velocity. I put this little hashtag up here, hash mark up here, which just is a prime. So it's just saying it's initial. And it's because we're going to have lots of subscripts here. So it's just the easiest way of doing that. Plus the momentum of the other thing, initial, is going to equal the momentum of the first thing, final, plus the momentum of the second thing, final. Well, that doesn't seem very helpful. And I just wrote my primes in the wrong spot. Sorry about that. Primes here. And let's see. That's the final. That's why. Okay. 1, 1, and 2. There we go. Let me write it over. Mass 1 V1 plus mass 2 V2 equals mass 1 V prime 1 plus mass 2 V prime 2. There. And that is why we use the primes. So this doesn't get confusing. So this is conservation of momentum for an elastic collision. Now, how these things work is that my velocities are still vector quantities. So if two things are going in the same direction and they never collide, well, initial is just going to equal the final picture. This becomes interesting when I have like a billiard ball and a billiard ball coming at each other. They collide and then they bounce off. And so we can take a look at what's happening to those momentums. So let's see. That's elastic. Inelastic. That just says they're sticking. So I would have mass 1, velocity 1, not volume, that's chemistry, plus mass 2, velocity 2, equals B prime. So the final velocity times the sum of the masses. And all this says is they've stuck together. So this is an elastic collision, and this is, I'm sorry, this is an inelastic collision. I don't know what the dogs were doing back there. And this is an elastic collision. So you're going to notice in my handout that there are pieces involved here with energy. So what I'm going to have you do is hold on to the handouts that I have. We'll work through the momentum pieces first, We're going to do energy, and then we'll come back and see how we can combine these two concepts. But the one thing I do want to emphasize is that when we're talking about things colliding together, what we're saying is that momentum is conserved so long as there is not an external force acting on something. So the most common one that we do for things sticking is that we say these are two cars. A car wreck is probably one of the more common ones. Two cars are traveling along a road, and they hit and they stick. And so we can use some of this information along with energy and forces to figure out how fast one of them was going. And that's when we get to really take advantage of this conservation of momentum. But that final velocity isn't referring to like this perpetual state of velocity, right? This is that split second after the collision, before that external force is slowing down this combined mass. So I think that is probably the hardest part to get our brains wrapped around, is what we're talking about, what portions of this is conserved. So let's see how this looks when we use it.